Okay, so we want to welcome everyone again to our seminar series. And today we have a very special guest, and you'll hear more about her guest speaker here pretty soon. But my task is to introduce the uh, student who is going to introduce our speaker. So our students introducer today is Hannah Castillo. I hope I'm pronouncing her name and stuff right. She is a junior chemistry major. She minors in math. That's pretty cool, Hannah. I actually did that too.
Oh, really?
Yes, yes. Did Randall, didn't you do like a double or something too?
No, yeah, I did chemistry major and math minor.
Yeah, yeah. Okay. Very
Yes,
nice. Yes.
yes, congratulations.
Yes. And so she is from Olney, I think, is the right
Only.
pronunciation, Maryland. She graduated from Spencerville Adventist Academy. And I gotta say, we have a lot of students from Spencerville. Thank you, Spencerville Academy. She plans to get into forensic chemistry, especially drug analysis, or an alternative would be doing analytical chemistry, which, basically forensic is kind of like. Um, and one of the things that I'm learning about her too is she's been playing the violin and the viola for over 12 years. Are you in the band here at Andrews or something? Or,
No, I'm not in the band. I was playing for like a couple praise teams every once in a while, but like I
oh,
just more play on the side now.
okay, all right. So this is Hannah Castillo, who will introduce our speaker today.
All right. So Dr. Chartanay Bonner studied at Tuskegee University for her undergrad years and then continued to receive her PhD in chemistry at Western Michigan University. Here she studied nanoparticles and their design, synthesis, and mainly their environmental impact. Her work focused on the exposure of silver nanoparticles and other heavy metal contaminants in bioremediation processes and sustainability. She is a woman of many accomplishments, having served as a graduate student associate ambassador during her years at Western Michigan and currently working as their graduate college research associate. She has also served as the National Organization for the Professional Advancement of Black Chemists and Chemical Engineers STEM Festival Chair. She is dedicated to promoting scientific discovery and research interest within the K-12 age group and stresses diversity and inclusion. So today, Dr. Bonner will discuss her work in the effects of silver nanoparticles within the environment as pollutants. This study involved the interaction of silver nanoparticles with heavy metal ions as the pollutants, and followed by the exposure to bacterial strains. This raises the need to observe the behavior of nanoparticles with other pollutants and their biological response, which is crucial in understanding the effects of metal pollutants in our environment. Please join me in welcoming Dr. Chartanay Bonner.
Right,
No,
thank,
I'm with Cindy and
right, thank you so much, Hannah. I know we're a little bit behind time because I think the class is over at 5:30. So I'll try to not hold you up too long and like looking at different things of the study.
Dr. Albert, do we just rinse it with water or?
Yeah, this is the egg stuff,
Yeah,
right?
the egg stuff.
That seemed to work pretty well for cake.
Okay.
So yes.
Science is going on, but just wait a minute and let it happen. All right, so let's go ahead and get started. If you can't hear me, just let me know and I'll adjust so we can kind of expand. So as Hannah was mentioning, my study focuses on nanoparticles and how they behave in our current environment.
Oh,
And it's really important to kind of understand how they move and interact and interject in our world. A lot of times when we hear nanoparticles, we think just on a workbench or inside, but it's really important to understand their commercial and cosmetic uses or production. So from antimicrobial use the way that we use them from silver nanoparticles in our cleaning products, the cosmetics that we use from our makeup and sunscreen, hopefully whenever the sun decides to come back out and play with us, even our clothes, the way that we stay dry and the different materials that are used for that, to our electronics, even just our computer screens that we're looking at now, our phone devices, even sporting goods, and the foods that we consume from preservatives are all controlled by nanoparticles and have been directly influenced by how they change or and are produced. But one of the big issues with that, is beautiful and wonderful they are with diversity, is they cause an issue with pollution in the environment. Now, as expansion and growth and development happens, there are unknown resources of how they're getting present in our environment and have been known to cause some toxicity effects or influence the health effect of our aquatic systems or even our biological systems. So a lot of times these are released through different manufacturing or improper disposal and different distribution. So as products break down over time and they change with their stability, that can lead to improper amounts of nanoparticles being present in our environment and us being unfamiliar with how they move or how they impact us as a whole. Now, when looking at that, we really want to think about how are these manufactured? How are they developed? Because they're so diverse in the way that you can expand how they can be used, we change their sizes by adjusting the different materials that are used, adjusting their surface charges. That can change how they interact with different species or absorption, and then even their shapes that helps improve their surface to volume ratio. That can be used for diverse fields that can be so helpful when we look at different sectors such as medical, energy, environmental, or even device development. So essentially from medicine distribution, nanomedicine and energy have changed how we structure and function in different systems. And the cost effectiveness of this has been extenuous from the way that we look at our lives and how they've changed. More importantly, just in 2019, nanoparticles were approximately had a global market impact about 8.5 billion. So if we think about that in structure, and it's due to increase about 13.1% over the next 5 years alone. So that's pretty expensive and pretty extensive when we think about how much has been used in the different areas that's been there. But unfortunately, because they're so diverse, only 7% is going toward the environmental sustainability or healthcare aspects of it, which can be kind of toxic because we don't really know how they're moving or how they're interacting with different species in our environment. So it's really important to understand what's happening and what will happen as they continue to interact with other components. So some of the impacts of manufacturing nanoparticles have been led to different production, distribution, and disposal regions. And that leads to our release in the environment. With that release, they end up accumulating in our water, air, and soil. But unfortunately, we don't know exactly how that's happening. Again, with those diverse properties and sizes, they have different routes than standard metals or standard materials that we use. So some of those primary challenges are how they break down over time when we see them. Also considering, sorry, give me 1 second, my paper's kind of covered up. How they break down over time. When they're present in the environment, multiple factors can impact their stability. So if they have different surface charges or different properties, they can absorb or be taken up very easily or compete with other species. They can alter bioavailability, and because they produce new species, that leads to that unknown toxicity. And one area that my study focused on was looking at the interaction with anthropogenic pollution, so other contaminants that are currently in the environment that have been added in. So when we think about some of our primary sources of nanoparticles and their toxicity, this comes directly from nanosilver, titanium dioxide, and carbon-based materials such as fullerenes and carbon nanotubes. Some studies have already started to look at the nanotoxicology of materials and how they behave or different negative impacts that they have had over time. So far as like nanosilver, It's used as purifiers, deodorants, and washing machines, but it can be impactful in our environment, how it's compacted or consumed in our soils and water that leads to contamination. Titanium dioxide, that's commonly in our sunscreens, makeups, and paints, are known to be genetically damaging, and with overexposure can cause oxidative stress. And even from the anti-aging creams that we use, or tear gas, or different textiles that possess carbon materials or carbon nanotubes, they have directly been known to be linked to cell and DNA damage across the cell membrane, or to cause different mutations in our system. So we really want to understand, how do these things work and how do they interact at certain concentrations and levels? So in my study, we chose to look at silver nanoparticles in particular, because they are one of the second most used nanoparticles that are currently used worldwide. Approximately 240 uses with 214 commercial uses. And not only is that concentrated in the United States, but globally, with markets in health and fitness, from medical, electronics, and even agriculture. And as you all know, we're in a COVID world right now. So between anything that you see that says antimicrobial, guess what? You've been exposed to some silver nanoparticles. So it's really important to understand how their behavior takes place and how they're staying stable or breaking down over time. So a good way to kind of like get an idea of this is look at the interaction of nanoparticles as they're in the environment, and some things that have already been seen. One of the biggest issues that we see is the absorption of these engineered nanoparticles, as they can be helpful in diverse fields. When they are not in their stable state, they can easily be absorbed by different species, from aquatic to microorganisms. And what happens is, as that time progresses, that can lead to the agglomeration, aggregation, or even the dissolution of these nanoparticles that can lead those metal centers to come out, and even more, cause mutation to happen or transformation. So that'll lead to oxidation properties, producing reactive oxygen species or other mutations of our standard nanoparticles that have a different behavior or route of exposure. So when we think about some studies that have already looked at nanoparticle environmental impact, Anne and colleagues have looked at how titanium dioxide and zinc oxide impact bacteria in soil. So they were able to see, by changing the concentration over time of these nanoparticles, it was actually act as an antimicrobial agent and reduce the growth of E. coli and B. subtilis bacterial strains. Not only that, Kai was able to look at how iron oxide nanoparticles in aquatic systems easily accumulated in different tissues and cells of species. So it led to being able to see how it directly impacted the percentage of surviving fish and how they grew over time, whether it was in their hatching phase or their growth phase. So even with that, we really want to understand how different particles or nanoparticles have different behaviors, and how they can be uptaken or impact the systems that they're in. But let's bring things a little bit closer to home. When we think about places like lakes that surround us, for example, Lake Erie, there are close to 5,000 toxic chemicals that are already entering lakes constantly. This is not even including nanoparticles that are starting to be introduced with their diverse fields. Some of these come from point source pollution from industrial waste and different discharges, human waste, organic matter from PCBs. If you take in environmental class, I know you heard about PCBs in Michigan and how they directly influence us. And we are actually just getting out these snowy seasons. So even considering the runoffs, the salts that are all there, and also heavy metals. Heavy metals are so intense in our water supply, we even have measurements of how we see them. So imagine how this can behave as they interact with nanoparticles as well. This can give us a whole new identity of toxic response or behaviors as they interact with our water, oil, and air. So as I mentioned earlier, some studies have already begun to look at some nanotoxicology behaviors and the impact of contaminants of nanoparticles and their toxicity as they're conjoined with different contaminants that are present in our environment. And this has led to different behaviors than independent are separate behaviors. So by interacting different nanoparticles, we have with different anthropogenic contaminants, we've seen reactive oxygen species be produced. We've seen alteration in oxidative stress. We've even seen changes in bioactivity, cell membrane disruption, and complete restructure of some of our aquatic systems in uptake and bioavailability. So it's really important to kind of really take a look at closer insight into how we can really measure these properties as contaminants are co-exposed, and we are co-exposed to them in our natural environment. So with that, we took a look deeper into some leading heavy metals that are commonly found in our water supply or in our environment and how they are uptake. Lead, cadmium, mercury should resonate pretty well on how we see different metals or things we know as heavy metal toxicity. Even when we talk about lead and cadmium and mercury, each one of them are known to have like some form of carcinogen and influence reproduction or lead to types of diseases or impairments, from impacting our brain to our lungs and our kidney failure. So we really want to understand, one, how are they toxic independently? And two, can nanoparticle exposure promote additional behavior of how this is happening? So this led to two primary research questions to ask. One, how does the presence of pollutants impact the stability of nanoparticles? So can they change how they're absorbed or how they function, how they move? And two, does the co-exposure of nanoparticles and anthropogenic pollutants alter individual antimicrobial response? So for example, we know that silver nanoparticles are antimicrobial agents. So can the presence of other contaminants impact its toxicity response in the environment? So to answer these, we've developed a hypothesis that looks at the toxicity of nanoscale materials, in particular silver nanoparticles, is impacted by the environment in which they are in and contaminants that they interact with. So by looking at silver nanoparticles, we're taking the assumption that depending on the environment that they're in, it can influence their stability and their function naturally. So to kind of like answer this or test this hypothesis, we looked at a couple objectives. One, the synthesis and characterization of various nanoparticles. What parameters of synthesis directly impact our stability and properties of nanoparticles that we see? Do they change how they function, how they move, and reproducibility? A lot of times, a lot of our products have these nanoparticles commercially, but again, they're not stable. So finding ways to improve their properties can be very essential to understand how they behave in the future as they start to decompose or break down. Two, determine the stability of silver nanoparticles upon exposure to anthropogenic pollutants such as heavy metals. Again, heavy metals are highly prevalent and they are easily replaced of other cationic species because of the positive charge. So it's really interesting to understand how those co-exposures together can be impactful in our environment as pollutants, since they're easily taken up. And then finally, comparing the antimicrobial properties of silver nanoparticles alone and comparison to silver ions and how these both can play a different role in toxicity that we see. All right, so as we look at this, we want to think about what are some of the factors that influence nanoparticles' properties. And again, that deals directly with tuning these properties. We have the ability to adjust them based on the materials and the concentrations that we use. So for example, when we think about tuning them, we can change their surface charges by the type of coating that we use, or even the capping agents that are present. We can change their surface energy by inhibiting or changing the growth patterns that by the different ligand species that we use or their concentration, and then also adjusting them for different research needs. Again, by changing their shapes and sizes, they can be more beneficial, whether it's catalytic studies or using it in detection of different species when we talk about nanoparticles such as silver and gold. So these are really important factors to kind of look at and understand how do these things impact their stability as well. So our first study looked at the synthesis and characterization of isotropic and anisotropic nanoparticles. So isotropic being one-dimensional and anisotropic being multidimensional, we were able to kind of see the behavior of nanoparticles over time. And the way we did that is by, one, investigating how synthetic protocols impact size, morphology, and stability of nanoparticles. And two, the characterization of identity of growth patterns and the stability of nanoparticles. So understanding how are they growing based on how they're characterized to support the data that we collected. So standardly, when producing nanoparticles, there's a simple step process that we use. Usually there's a precursor that you start with that's reduced, that allows nucleation and growth to occur, that allow us to have a nanoparticle solution over time. And this is done by different synthetic methods. These methods can consist of wet chemical synthesis, thermal decomposition, which is the application of high heat, polio process, biological or sol gel methods. Now, a lot of these are adjusted based on how we are reducing or changing or using different attachment species for this. So this can be done by what precursor we're using, the solvents that are present to keep them stable, our ligand species to kind of like influence the growth patterns that we have or the stability of our system, and also concentration. Concentration can sometimes impact the sizes that we make or the length that we have by changing the kinetic behavior, our pH, as well as our temperature. So all these things directly influence how we're able to reduce, store, and allow the nucleation and growth of our nanoparticles. And the way that we can observe these things are based on characterization techniques from electronic or spectroscopic technologies, thermodynamic studies, or optical imaging. And the nanoparticles are so cool because it allows us to see their different properties as they change with our different studies. However, as mentioned before, this does lead to some primary challenges that need to be adjusted over time, whether that's monodispersity, so how stable they are, and are they even in the sizes? Because if they're not even in sizes, we get different properties. Size and shape control. Reproducibility, so how often can we get it at a cost-effective rate? High temperatures, so as high temperatures occur, we're using a lot more energy, and expensive materials. So finding a way to standardize this where we can have stable properties that do not dissolute or break down as easy so we can use them for studies. So one of the first ones we looked at was the synthesis of silver nanoparticles. And this was a wet chemical synthesis method where we just used silver nitrate and water. And we were able to reduce it with sodium borohydride, a strong reducing agent, and cap it with a citrate ion. And what happened is, as this set over time, the charge on that silver became silver 0, and we were able to produce silver nanoparticles that end up reflecting a qualitative property of a yellow color that kind of indicated that we had produced silver nanoparticles. One of the cool things about silver as well, unlike silver ions, silver nanoparticles have surface plasmon resonance. So that allows us to have a peek to kind of tell where or the size of our nanoparticles that were produced. So we were able to use a UV vis to kind of like identify and indicate the stability and the size and uniformity of these nanoparticles. And based on this peak, we could tell that it's right around 395 nanoparticles that indicates, based on past studies, that it's stable, and we've produced about 4 nanometer nanoparticles. To support that as well, we use a TEM image, which is just transmission electron microscopy, to kind of show that our particles were dispersed in size and uniformity that can be used as a stable method of nanoparticles to be used and studied for research. Another study we looked at, or synthesis route we looked at, was for ruthenium nanoparticles using thermal decomposition. So by using a ruthenium precursor in the presence of indodecyl sulfide and a diphenyl ether solvent, so it can be done at higher temperatures over time, we were able to kind of break down and produce ruthenium nanoparticles that were spherical with monodiverse in high yield. So as you can see from the TEM image, again, we were able to make these particles, and our support of that was through our TEM. But again, because of those high temperatures, we wanted to find a way of trying to build shapes without having to use such extreme methods. So what we did as well is we tried to find out what are different ways that ligand species can help support the growth of these nanoparticles by changing their shapes and sizes. So at room temperature, we also looked at ruthenium chloride in the presence of a thioligand and strong reducing agent at room temperature with different size ligand thiol species. And this allowed us to produce different nanoparticles of ruthenium with different shapes and sizes. So ruthenium grows in an HCP growth pattern on its surface. So it is promoted for rods and spheres to be formed. So a lot of times by using those different ligand species, we're able to kind of control the pathway that they grow and the different species that we have based on the chain length. So to compare that, we also took a look at thermal decomposition of palladium. So palladium nanoparticles at elevated temperatures in toluene instead, we were able to see as well that it produced our nanoparticles, but again, different sizes with different, a little bit more dispersed than ruthenium and silver nanoparticles. And for these, again, they grow at a different facial center cubic rate. So this changes the amount that we see in the growth pattern. So to understand like the pathway that this is done with our ligand species as well, we looked at various ligands to kind of see the growth pattern that we would achieve with those ligands. So unlike ruthenium, because it's face-centered cubic, it grows in different patterns. So we are able to get different shapes based on that metal species. But again, some of these are agglomerated and broken down, and there's not necessarily any uniformity in size. But we were able to get various shapes based on that ligand species. So we were able to tell the impact of our ligands play a direct role on the synthesis of these methods and how they grow, which also shows that if we're making nanoparticle with different pathways and growth, they have different surface properties of how they interact. So again, we were able to develop isotropic and anisotropic nanoparticles at room temperature that explored the stability and shape control based on that thiol ligand over time. One last method we looked at of synthesis was using quantum dots. So understanding how thermal decomposition as well, but quantum dots using a selenium precursor in the presence of octadecene and trioctophosphine. We use a hot injection method. So at 225 degrees, we were able to inject selenium solution after cadmium oxide had reached ideal temperature. And based on that, we were able to see like how we could produce different nanoparticles or quantum dots at those temperatures that were there, which led to a little hollow structure that we can see. And with these, again, we're using toxic metals. So if the stability of these are not uniform and stable, as we can see here sometimes, that can directly influence the release of those metal centers or some toxic responses that happen. And these are a little bit more complex conditions of development. And even though they're used in different areas of study that are diverse. So in summary, we were able to see that synthesis and reaction conditions dictate the properties of nanoparticles that we have, and they can be directly influenced based on our time, temperature, and ligand species, because these things directly impact the stability, the reduction of our metal, and our dispersity of shape. And these ligand species can also influence the nanoparticles that are formed. So again, based on temperature, we could see that we were able to have increased yields or different structures in the spherical shapes. We could also see that the ligand species influence how we had diversity in our shapes in the compositions. So from rods to cubes and spheres, we were able to produce in this method. But again, even by looking at these, you should be able to see that they're diverse in size and how they impact the way that they'll interact in research or in different studies. So with that, it's really important to kind of look at the properties and the influence of these alone on nanoparticles. So a few studies have also been done to look at how changing the size dependency, shape, and even the surface coating can influence the toxicity or the impact of nanoparticles in the environment. For example, Avast looked at different nanoparticles of silver nanoparticles from 10 nanometers to 80 nanometers and was able to see the difference between how they impacted the growth of bacterial strains. And again, the smaller nanoparticles led to higher toxicity, but at the same time, they were discovered by different rates of how this happens. And opposite of that, Gilbertson was able to look at copper nanopowder sheets versus bulk species to compare how changing that surface growth directly impact the reactivity or the antimicrobial response of copper as well. So again, even though different pathways in different species, we're able to see how this is changing the pathways of growth that we're seeing. And even by that different coating agent for looking at electrostatic versus polymer growth, using reactive oxygen species were grown in Yang's study to kind of look at how toxic are the uptake of nanoparticles based on reactivity and dissolution within C. elegans. So it's really important to kind of pay attention to all these different factors that change with our nanoparticles development. So this led to the meat of our study by looking at the impact of heavy metal ions on the antimicrobial properties of silver nanoparticles itself. So here, our research objectives were to determine the stability of monodispersed silver nanoparticles upon exposure to heavy metal ions, cadmium, mercury, and lead. We also investigated the impact of heavy metals on antimicrobial response of silver nanoparticles towards gram-positive Staph aureus and gram-negative E. coli. And then finally, we compared the antimicrobial response of silver ions and silver nanoparticles, as a lot of times the toxic response of silver nanoparticles is expected to come from silver ions. We wanted to compare to see if there's a difference in the behavior that we saw as that occurred. So again, we look at silver because it's so diverse from its broad spectrum of activity, its efficiency, its low cost, and its superior antimicrobial agent properties. So again, that surface plasma resonant properties that allows us to see the shift in sizes and color and shapes is very essential because it helps us tune the properties of nanoparticles and easily detect what happens at the surface. So that helps us understand about its stability and how can it interact with other species over time. So this allowed us to develop the scope of our study. We looked at citrate-coated silver nanoparticles with a negative charge on its surface that can interact with bacterial strains in two routes primarily known. One, from the direct uptake of silver nanoparticles to the surface of bacterial strains, or two, the release of silver ions, Ag+, that can be uptake or cause damage of the bacterial cells. But these are studies that have been done. We're looking at them independently. For us, we also wanted to take a look at how does cadmium 2+, mercury 2+, and lead 2+ impact our stability of silver nanoparticles over time. So we observed how that change in stability occurred and then what influence that had on bacterial strain growth. And we were able to do that by looking at optical density studies over time in a 20-hour time frame over 5-hour increments. All right, so the importance of bacteria, a lot of times, we know we have gram-positive and gram-negative that have different surfaces or thickness and have different ways of how they uptake and interact with bacterials, with different pollutants. One of the cool things about having bacteria in our environment is that it's a natural bioremediator. So it helps clean up the environment a lot of times, especially with heavy metals. They can release them in new ways. They can help absorb different contaminants and then release them to they be more safe and more helpful for the environment. But again, if we don't understand how these things are interacting, they can also be changed by the presence of these nanoparticles, as we know that silver is an antimicrobial agent. So if we look at silver in itself, again, there's two primary routes that we see. One is the exposure can be through penetration through the cell wall. If you look at how it attaches on the actual cell wall, and a lot of times that has to do with the size of it, and those nanoparticles can penetrate through. That can lead to cell death or damage and produce reactive oxygen species through either the nanoparticles itself or silver ions. And another way is the release of the metal center. So based on that size, a lot of times it's known to release through and lead to death of bacterial cells. And again, this is influenced by 5 primary factors. 1, surface coating, whether it's steric or electrostatic. In our case, we're looking at electrostatic because we have that citrate coated and we have these heavy metals that are there with a positive charge. The release of the metal ion, that's why we're comparing those silver nanoparticles and silver ions, the size and shape and morphology, the exposure media, and the interaction with chemical contaminants. So as we look at silver nanoparticles in this study as a whole, we were able to see, again, that our synthesis of nanoparticles were stable initially with that ideal peak, a uniform peak that shows that the nanoparticles were monodispersed and easy to see with the citrate coating on the outside. As we added our cations with 2+ charges, we looked at the change in concentration in time to kind of see if any of these changes occurred from aggregation, agglomeration, dissolution, or complexity. In comparison of cadmium, mercury, and lead, each of them showed a different reflection of how they behaved in the presence of silver. And again, as a way to kind of manage seeing the changes in time, we kind of compared it to our control of silver alone. As you can see in the presence of each one of them, there's a slight red shift towards the right or higher numbers of those wavelengths, which kind of like indicates that there's some aggregation that's taking place. And even with cadmium, there's starting to be a quenching, so a decrease in that peak and broadening. That broadening of that peak indicates that we're starting to see some aggregation of these nanoparticles that are taking place. In the case of mercury, there's a huge dissolution of these nanoparticles as that peak is almost completely quenched immediately at all concentrations and broadened out. So again, it tells us that it's a change in our stability of these nanoparticles at different concentrations over time. And for these were all done at about 10 hours, 10, 15 hours to kind of compare what they look like. And then when we look at lead, again, there's a shift in broadening of peak, but we also see that secondary peak starting to form. So that can be an indication of kind of a different form or agglomeration or complexity of our nanoparticles that are there. So all these things help give an insight of our silver nanoparticles are not as stable as what we look at naturally, which is expected because of that charge on that surface. A lot of these things are naturally attached. Mercury in particular is known to attach to silver nanoparticles often and to form a different complex. So it's really important to kind of understand or pay attention to how this shifts based on that surface plasma resonance. All right, so from that, we were able to kind of compare antimicrobial impact of silver nanoparticles in each heavy metal. So by first looking at Staph aureus and cadmium, we can see over time, over that 20-hour time frame, that there's a difference in our bacterial strain growth. So in itself, cadmium had the least amount of toxicity to Staph aureus on its own, and silver nanoparticles in silver being the most toxic. So as our control groups independently, they all had different responses. However, upon co-exposure, we can see that cadmium and silver nanoparticles were still similar to silver nanoparticles alone, and cadmium and silver ions also did the same thing, following the behavior of silver ions alone. So it kind of tells us that there's something, even though that cadmium is there, that it's kind of limiting that availability for that cadmium with those bacterial strains. Now, if we look at our TEM here, it looks at 15 hours of silver nanoparticle upon exposure to cadmium. Again, we could see some of those broadening of those nanoparticles over time. And then we kind of took that same nanoparticle co-exposure to look at how does that attach to the surface of Staph aureus. And if we look here at different points, we can kind of see that at the surface of these bacterial strains for that Staph aureus in this sphere straight, they're starting to break down at the surface. So it shows us that there is some attachment of those nanoparticles at that surface over time. All right. And even when we look at cadmium and silver nanoparticles in the presence of E. coli, which is our gram-negative bacteria, again, we see similar data, but cadmium is even less toxic. In all of our species are a little bit less toxic than the gram-positive, partially because of that cell wall of our bacteria strains, which we expect to see. And again, we see kind of a similar behavior. Initially, independently, we see a difference in each one of our control groups. But as we look at co-exposure, they're similar to those silver nanoparticles or silver ions alone. And there's a slight reduction in our silver nanotoxicity, but not necessarily studied enough to kind of see a difference there just yet. And again, if we look at that cell of that E. coli, we can see that these nanoparticles are concentrated all around that cell and starting to break it down, which we expect to see because those are those two pathways we want to see. But one thing that is interesting is there is a difference between that silver nanoparticle and silver ions. So that kind of indicates that we're not only seeing silver ions at the surface, but there could be something else that's going on and how it's penetrating the cell that's changing that toxicity. All right, and we were also able to do the same identity when we look at silver nanoparticles and mercury over time. Now, unlike cadmium, mercury is extremely toxic to our bacterial strains and is easily to be uptaken and to kind of like transform and break down. It's even more toxic than silver nanoparticles and very similar to silver ions alone. But what's interesting again, when we see silver nanoparticles and mercury in co-exposure, it still follows the trend similar to just silver nanoparticles alone. So kind of indicating that these nanoparticles could be blocking the availability for these metals close to the bacterial cell or the uptake of the bacteria. So here we can also see like a TEM that's a breaking down of these nanoparticles. They're not as uniform and they have been diluted much more, again, supported by that UV vis we saw. And if we look at the Staph aureus, again, there's a breakdown in that growth of those bacteria. So you can kind of see it a little bit more in how they're not as big as our other one, but we do still see them kind of concentrated with nanoparticles around in that dissolution a little bit. So it kind of shows us that, yes, we've seen, but there is some type of difference that's occurring with the co-exposure than independently. Okay. And then even in the presence of E. coli, but still pretty toxic as a whole. We do see that in co-exposure to both of these, we still see that same behavior that occurred the first time. Okay, so that changes how these things are growing and how they're concentrating at the cell. And if we look at this TEM image, again, we can see it concentrated on certain areas of how it's distorted the bacteria, indicating that cell damage is occurring and it's starting to break down over time. All right, and then the last one we looked at was lead. So we looked at lead ions with silver nanoparticles over time and looking at, again, over that 20-hour time frame. And remember that lead caused a little like secondary peak and breakdown of some of those things we see. Lead was our least toxic metal out of all of our control groups in comparison to silver, lead, and cadmium. And again, when it was in the presence of silver nanoparticles, though, and silver ions, there was still a more significant toxicity. So we can kind of see that it's changing the availability of not more so the silver nanoparticles, but changing the toxicity of our heavy metals and their toxic response to bacterial strains alone. And a lot of this could be due to the competition and the availability of these metals at that surface. All right, and then our final one, looking at silver nanoparticles and lead in the presence of E. coli. So for this one, again, we don't see that cell broken down as much, but again, we can see based on that E. coli structure that these nanoparticles are close by and they're able to kind of like surface, attach to that surface of these bacterial strains, even in E. coli. So it takes a little bit more to break it down, but it is causing some type of reduction in growth and change in that structure. So again, we can see that in comparison to these three, there's a change in the different growth areas that we see. All right, so just to take a closer look at the different areas and how these things occur, we kind of compared the growth phase of all three. So we looked at bacterial strain growth at the 5-hour time frame and compared what are some different things that we can kind of see. So we used about 25 micrograms of milliliters of silver nanoparticles in the comparison of cadmium, mercury, and lead. And again, we kind of see that with mercury and silver, there was a little bit more toxicity. And then with silver and cadmium, a little bit more than lead and silver alone. All right. And that was for our Staph aureus. And in the presence of E. coli, same kind of concept that we see here. There's a slight change in how they grow, but we do still see the same patterns, that they become more similar to silver nanoparticles and the elements than their control groups are alone. So in conclusion, we were able to kind of assume that what chemical procedures were found to be effective in controlling transition metal nanoparticle shape and collide uniformity. So as we made those silver nanoparticles, or we were able to do it at like extreme temperatures, we are able to get like more controlled shapes and sizes of our nanoparticles. But again, it takes adjusting them to get that reproducibility and availability of growth. We also see that silver nanoparticles influence the availability of heavy metals to bacterial strains. So thinking about the hypothesis that silver nanoparticles are going to change based on the environment that they're in that exposure. Well, what happens was, from our data, we kind of see that the silver nanoparticles actually inhibit, or it looks like it inhibits the uptake of some of those heavy metals towards the bacterial strain and actually have its antimicrobial properties being seen. And our last conclusion that we came up with from this data was the co-exposure of heavy metals in silver nanoparticles were less toxic than the presence of silver ions and heavy metals alone. So that kind of indicates that it can't just be the silver nanoparticles alone. It could be based on the concentration or the amount or the route that's being taken. So based on that surface coating and how these things are changing that interaction. So this led to kind of considering some other studies to think about in the future of how this can help. So we could investigate the antimicrobial behavior towards different bacterial strains. Based on the bacterial strains, some of these are known to uptake metals differently or break them down based on bioaccumulation or transform them in the environment. So based on the different bacterial strains, we can see different responses of how that occurs. We can also look at understanding the antimicrobial behavior of various nanoparticles with variation in size, shape, and coating. Again, these can change the attraction to that surface or the absorption or changing of how they interact with those bacterial strains, which can essentially lead to different responses than what we see here currently. And then we can examine the difference in binding interactions with other metal species are present. So we can look more closely at different analytical techniques to kind of understand, well, what binding do we see taking place and how can what is really occurring at that surface level with those different charges? Because again, we do know that electrostatic attraction could be occurring, but that could be only one aspect of what we're seeing of how this uptake is happening. And then finally, studying the toxic response of nanoparticles and other anthropogenic pollutants present within aquatic systems. So understanding how different medias in different areas can occur when this happens. All right, so with that, I want to thank Dr. Shereen Obear from Western Michigan University, and also some of my past professors at Tuskegee University, and also funding opportunities from the Michigan Alliance for Graduate Education and the Professoriate from Michigan AGAP, and then the Martin Luther King, Cesar Chavez, Rosa Parks Future Faculty Fellowship. And with that, I would like to thank each and every one of you guys for coming and listening. Are there any questions?
Okay, let's give Dr. Bonner a round of applause. And any questions that you guys have? In fact, you have two options. One is putting it in the chat, as you know, or just directly unmuting yourself and asking the question. So I have a question to get things started. In general, the comparison between the silver ion and the silver nanoparticle, how does their toxicity differ in general? Is one more toxic than the other, or is it dependent on the bacterial species that it's involved?
So that's a really good question. A lot of times in standard studies as control based on the concentration, silver ions do tend to be more toxic. But what happens is based on their size, the bigger nanoparticles that you have of silver, they're known to either release those ions in itself. So it kind of like has a more direct route based on those surface coating and bindings. But some studies have shown that smaller nanoparticles, so like kind of the ones that I was looking at between that 2 and 5 nanometer range, don't only function as the release of silver ions, but they have another way of presenting toxicity. So even going back to that study about Avaska, he compared silver ions, which were right next to it, but silver ions and nanoparticles of the smallest size both had similar toxicity, but their toxic response was different based on ions released in size. But the bigger ones were less toxic, but released those metals. So a lot of times that has to do with concentration and availability, but ultimately silver ions are more toxic in itself.
Oh, okay. So it's possible, from what I'm hearing you say, it's possible that the silver nanoparticles themselves is a source of silver ions. Is that part of what you're saying? Okay. Okay.
So let me see if I can go back a little bit. So even if we look here, the two primary routes that are known are based on either those silver ions being released out of silver nanoparticles, or depending on how small that size is or that shape, because it changes the availability for it to absorb or be uptaken, it'll absorb into the cell.
Okay.
So a lot of times that directly influences that toxic response.
Okay. And all of your studies were done with silver nanoparticles with citrate as the ligand, correct?
Yep, sodium citrate.
So and I'm assuming that's sort of the typical silver nanoparticle.
So standardly, that's one. And then another one is often you'll see like polymeric growth on the surface, or if people do biological synthesis of them, but usually those are the two ways, and primarily it is citrate. That's usually that capping agent.
And so that's the one that you would say is found in consumer materials?
Yep, in some of them.
Okay. Yeah, it's really interesting to see how, I don't know the historical, sequence in terms of like when silver nanoparticles started really getting into consumer products and stuff, but it's really interesting to see how many products now contain that, and that I don't know how much actual toxicity studies have been done, like some of the things that you're doing and proposing to continue doing.
Right. So that's one of the biggest things about it. It's just starting to expand, like nanotoxicology articles. And I think probably in the past, maybe 7-10 years or so, that they're just starting to look at different routes of exposure that's happened. And one of the most recent papers that kind of looks at overall in the co-exposure of these things, whereas back in like 2017, I believe, or 2015, to kind of like summarize some of these behaviors that have been taking place that we don't look much into, because initially, because it's smaller and it's assumed that the concentration is so less, it's not really looked at as seeing it as you were saying, like just the ions itself or the metals itself being released. But because they are smaller and they do have that easily ability to be uptaken, that can change the accumulation over time. So that's why it's really important to kind of think about those routes of exposure or how stable they are over time.
Right, right. Dr. Randall, I think, has a question.
So I hope my PChem2 lab students are paying attention to the nanoparticle spectra here. So I was just wondering how the spectra of like the non-spherical nanoparticles, I think there were some like cubic ones and then also some rod-shaped ones. Did those have kind of the normal little peak shapes there?
Hmm.
So that's the.
I'm sorry. Yep, this is the one you're looking for, right?
That's fine. So those are the different shapes then.
Yep. So often, based on how that peak is, you're either going to get a different shape or size depending on where it shows up. So a lot of times, like rods, for example, because we see that long area and then we see that shorter side piece, that one's going to give us two peaks often. So we're able to see like the way that it grows. So depending on the structure of it, that's what changes the peak often. And we can kind of tell based on like the surface chemistry.
I see. Okay. Okay, very good. Thank you. So
No
really, so basically, it just the peak the peak just moves around basically in some sort of a dependence on the size. It has the normal shape, so to speak.
Yep. And then sometimes you'll see like a secondary peak depending on like how it's growing.
Yeah. Okay. All right. Got it.
Okay. Very
Thank
good.
you.
Any other questions? So what you were mentioning that silver nanoparticles are like the second largest in that, I guess if you could call it industry or sector. What are some of the other more prevalent commercial nanoparticles?
Some of so the top leading one is carbon-based nanomaterials. So that's the number one. And then like titanium as well is leading. And I believe iron oxide or iron magnetic nanoparticles.
Ah, okay. I see. Very nice. Okay, well, we want to go ahead and give you another round of applause. Thank you so much. And I have to tell you guys that we had to change our speaker because the original speaker couldn't make it. In fact, I think it's because of what's happening in Texas. So his lab and all of that was impacted. And so, you know, he's consumed with trying to get that taken care of. And so Dr. Bonner stepped in with like a couple of days notice. So keep that in mind. I mean, she did a fantastic job with only, you know, a few days notice. So that was really gracious of you and you did a great job. Thank you so much. Thank you so much.
Thank you for the last minute save there. We appreciate it.
Yes.
Well, thank you for having me.
All right. Have a wonderful evening.
Thanks. You too.
Okay. Bye-bye.
Bye.